Okay, so we're talking about the for loop, the for range, and this one operates like the one you saw in Python that made it easy to loop over a list of objects or a list of variables, where you would just go like for item in items, and then in the for code block you would do something with that item, and each time it loops it goes on to the next item. You don't have to worry about indexing or anything like that. So C++ included the for range in C++ 11, so it's been in C++ since 2011. Before we do that, we are going to cover one example with the regular for loop to show you how to loop a string. So okay, so we have the header here. Let me see here. Take this stuff off. Okay, so we have write a void function, so void loops string with maybe not index but for loop. And in header files in C++, we don't use the using in header files, because since they are included in many files, if we do that, then we are going to be using that statement in code where we might not need it. So we opt for this syntax. So we say string. That way we are including string, and we're helping the compiler find string by prefixing the string data type with the string class with the stud namespace. And you see our code is okay, it doesn't get confused. We come back to the CPP. Here I can say using string, because the CPP files are not included all over the place, so that's why we can do that here. So this string and vector are only going to be in the scope of this file. Okay, so this function uses a for loop to iterate and display characters in the string. Okay, so before we write the code, so from most programming languages, when you save string to memory, it's a sequence of characters, and there's two variables, or not two variables, two counts that we are interested in: the index and the count. So the count is like what size is this string. In this case, we can see that the size of the string Joe is 3. In most major programming languages, indexes start at 0. Okay, so we keep that in mind, and we can say, okay, so if we want to access J, assuming our string variable is str, then we can say str of 0 and access J for Joe, right? So with index 0. And if we want to access the next one, it's 1 and 2, but we never get to 3, because if we get to 3, then we are beyond the memory, and we may run into issues. Like more than likely, we're going to get an error, right? So we don't want to do that. So we have to write code that keeps us within 0 and within the 2 boundary. So in the string class, programmers have written some code for us so we can query the string, right? So we can ask it for the size. So if we say, hey, string, what size are you? And then it tells us, okay, and then if we hover over this, it returns the number of characters in the string, right? So if it was Joe, it would return the number 3. And remember, the for loop has 3 sections. We have the initializer. I'll explain size of t in a little bit. So we say size of t equals 0. And then the condition is the next one. So we say while I less than And here is where we can say, well, we only want to iterate 0, 1, 2. So we only want to iterate up to 2 starting at 0, right? So we can say, okay, so while I less than string.size, right? I cannot be equal to size, because if it is, then we are going to be trying to access this address over here, which is not in our string, and we might run into issues. And then we increment I. Okay, so what is this size of t guy? So if it's an unsigned integer, and if we look at this guy, so size returns size of t. So let me explain. So the size of t represents a very large number, unsigned integer, right? So if we use integer, remember integer supports negatives and positives, and I think it goes up to like 2.1 billion, but unsigned integer does not support negatives, so then it goes to what, 4.2 billion characters. So and this is what this size of t represents, unsigned int. So nothing stops us from doing this. Like, notice we don't get any curly brace, any underscores here, and everything seems okay. Like, we don't get in trouble. But if we come here and we compile our example, we go to examples, for range, and I can just compile this piece, the library. So the library only compiles .h and .cpp. So I can go build, and let me pull this. And notice in the build, like, it's trying to point something out to us. So if we go here and then we scroll over here to the right, it's saying that comparison of integer expressions, different signedness. So meaning like int to unsigned int. So chances are our code won't break, like for the examples we're doing here, but if it's in a real production system, then we can't do this. Like, if you sit down for a code review with a more senior programmer, then they're going to bring this up. They're going to be like, well, I mean, we want to make sure we use the correct type here, size of t. That way, if this size is larger than what an integer can hold, our integer won't circle around and then become like a negative, and then our loop's going to get all confused, okay? Size of t with strings, right? So size of t with strings, like or with vectors. Like when we introduce vectors in a couple of weeks, we will want to stick to this convention, to this data type here, and that'll keep us away from trouble. So let me go here, build, and then I come here. So notice now I don't have any warnings. The warning is gone because now I'm comparing unsigned integer to unsigned integer. So I won't get into a situation where my unsigned integer is bigger than my integer, and then the integer's gonna return a negative number, and then our loop's just not gonna work. So any other questions here? So Tim was asking, like, do we use size of t for every time we set up the accumulator? Usually if we are using the string or the vector and we are querying the size, and yes, we want to make sure that we match the signedness type. That way we don't get any warnings or run into issues in the future. Okay, so here we just simply want to display a string like this, okay, in one line. So let me see, we don't have IOStream here, so let's include IOStream. And here I can say using stud cout. Now I can come here and say cout, and remember that we can do str, this string right here that's coming in, add index I, and then a new line, and it'll iterate 3 times, right? So the first time I is 0, we increment I with this code right here, and then the second time I is 1, and then the third time I is 2, and then the fourth time it comes here, and I is 3, but I is not less than string.size, which is 3, so then our loop doesn't execute again and jumps and exits this function. So we won't get into issues with going beyond the string memory. And we can come to our main. Again, this returns void, thus we can't create a test case, but we can call that function. So loop string with for loop. Let me create a string here. I guess Joe, and then I passed in that string as a parameter. And now I'm going to use my loop in main, so I go ahead and execute the program. And we have JOE. A very simple example, but it's just to show you size of t, and again remind you how to set up a for loop, but then to compare it with the for range, which is the next example. Like we'll see that the for range, we don't have to worry about, well, I mean, index and counts and all that. And that's our next example. But before I move on, any questions on this block of code right here? Okay, so no questions, so we can move on for range.h. Oh, also, before I forget. Okay, before I forget, Jose, let me just, I'm sorry I wasn't at the office hour today. My brother had car trouble, so I had to go pick him up. So that's why I didn't make it back in time. So if anybody was waiting for me, I'm sorry. And I didn't have my phone to like log on to the call, so I apologize for that. Okay, Jose, you can go ahead. No, I just, yeah, usually like this. Yeah, I overlooked that. Usually in CPP, we want to do this because we'll be looking at a lot of code. We'll be looking at the function signature or header or prototype, and then the function code. And seeing a lot of this stuff will make our eyes sore. So maybe we can even do the using size of t up here also. For this one, it's okay because usually for the header, we don't have a lot of lines of code, but it's best practices to do this in the header. But yeah, that's a good point. Like over here, we want to minimize all the namespace stuff. Okay, so the next one, we write another void function and loop string with a for range. And then you'll see, when C++ realize that legacy programmers aren't going to live forever, and then to recruit younger programmers, and that to make the language easier to pick up, right? So we can say for, we can use the word auto, and we can say for, I guess, s in string. And then we can simply say cout s. So we'll read it in English. Oops, not s here, new. For each character in str, display it to screen and write a new line. And notice here, like we don't have to worry about index and size and comparisons and all that. We just use the syntax, and behind the scenes, C++ takes care of everything for us. And we can go back to main.cpp, and we can say loop with for ranged name. and run in terminal. And we get the same result. And the same amount, the same lengths of code, right? But it's a lot easier. Like we can just say like for each string in str, then output each one, write a new line until there's no more characters. So we saw the output here, JOE, and that's the for range loop, which makes it a lot easier. And thankfully, right? Because before that, like C++ was losing ground to the Pythons and C Sharps and Javas, right? So then they had to make a change, and they did. So questions here, like on the for range. We will cover more about the for ranged when we talk about functions. Like we'll see like how we can modify characters that are in the string using a for ranged, and how we can avoid or how we can prevent characters from being modified in the for range loop. So questions? Okay, so no questions. Okay, so that takes care of that. Close all. Okay, so no questions there. So then let's go and talk about functions. So I mean, we've been using functions mainly because I wanted to emphasize the importance of testing. And I'm sure by now you can appreciate those few extra lines of code you write for the test case really pay off, because they validate your code and make sure your code's working. By the time you use it in main, you're very confident that your code works properly, which is what we're after as developers. We want to produce high quality code. Not only do we want to do that, right? We want to organize our code. Let me make this larger. It's too small. We want to organize our code, and we can do that by using a divide and conquer approach. And then I'm sure you have noticed that so far in most of our programs, the main is small. Like instead of seeing this code in main, then we are seeing something like this in main. And this concept is known as encapsulation, which means we hide away the details of our program. And that means we hide away the complexity of our program. I know our programs have been simple so far, but point being is like we focus on writing code in functions, and then we use main to call those functions. And usually those functions will work with each other to run a program. So that's what encapsulation means, right? So encapsulate. And then we can shoot for code reuse. We don't have to write the same code all over our program, because if we do that and our program starts growing even to like thousands of lines of code, and we have like a block that we use all over the place, and then the logic changes for that block, then we would have to find all those locations where we use that block, and more than likely we wouldn't find them all. So that's why functions help us, right? Because if we know we need to change our code, then we have to just change it in one place instead of a lot of different places. And then I know that I've emphasized unit testing, so functions, return value functions help us with unit testing. And then they also help us with extending our program. So we can add features to our program without fear of breaking it, and we can fix bugs, right? So maintainability. So with functions and unit testing combined, then we can fix bugs easier and we can add features easier, because as we develop code, we write more test cases. So we have a bank of test cases for our program. And you will see that once we start developing the tic-tac-toe program, where you start collecting all those test cases, and as you're adding more code, you add code confidently because you have test cases to make sure that if you break something, they're gonna alert you. So that's why we use functions, right? So also, while I'm here, I have this I'll put or test. So the C++ core library, we can write code in main or in functions that uses a core library, and we can use the standard library, in main or in test. But the way we've been doing it is we write code in .h and .cpp files, or header files and implementation files, and we are creating our own user-defined libraries. So if you recall, I went here to the for range and I said, in CMake, I said, let me compile the library. So notice we have a library. It's only 2 files, but it's a user-defined library that has this functionality. We can loop a string with a for loop or with a for range loop. And we've been doing that for all the examples, and you've been doing that for your homework assignment. So you should define libraries, and then we access through main. If you work in programming, then you will more than likely also have another block over here, and that'll be like third-party libraries, like third-party tools that maybe somebody has, like a graphics library or a component library for creating Windows applications where you just drag and drop forms and buttons, and you don't have to program that with Windows. You just use somebody else's library, and then you can go into rapid application development. So what we are learning here will help you in the future. Okay, so I'm not just trying to make you do extra work. Like, this is how you can become a good developer, and then your developing skills here will scale to like a lot of lines of code. They won't just work for small programs, right? So that's why I always stay away from writing code in main. For code that should go in functions or classes, we should never write in main. Okay. Any questions on the reasoning for using functions? And it makes sense, right? So organize, encapsulate, code reuse, unit testing, maintainability, and extendability. Okay, so no questions. So then by now, like Python, you know that C++ has functions that do not return a value. These are the void functions. It does not return a value. And then we have functions that return a value. And by now we know that we have to be very specific with the value return functions. Do you want to return a string, a bool, an integer, a double? Like, we have to tell the compiler step by step what we want. So the compiler will understand what we are wanting to do. Void functions, we usually use them to display. Okay, I'll make that large. Display, write to file, maybe send files over network. That includes internet and what have you. So we display, write to files, send files over network. And value return functions, we usually get data via parameters, and we process that data, and then we return maybe calculated or formatted data or something like that, right? Depending on what that function does. And I'm pretty sure everyone knows to reuse a function, we need to include the files that contains the function. Yep. Yeah, just like we do here in main. So here in main, in the example I was working, I have to include for ranged. If I wanted to use for ranged in some other file, then I would have to include for ranged, so that that region of code understands and knows where the functions I want to use are. Obviously, we would have to set up the CMake too. So this CMake's what glues everything together. Okay. So that's why you don't have to worry about like how's all that stuff working. I don't think that's too important right now. It's more important for you all to learn the C++ syntax and the concepts of programming, and trying to figure out how to put this all together. All right. Okay, so let me come back here. So void functions do not return a value, and let's go to a void function. We stick to this example for range.cpp. We can simply say return here, as long as we don't put something here. Like return means, hey, just return. But since we've not been using it, then we can imply that C++ is like, oh, okay, so I reached the curly brace, so I'm going to return. Sometimes if we are using conditional statements, and maybe here, like a simple example is string dot empty. So if the string is empty, then I don't really have any business going to the rest of the function. So then I could simply say return, like don't come here. Especially if this had some logic that depending on the string having some data, then we could do something like this, like to exit, and it would just execute up to this point, and then it would just go back to main where it was called. Okay, so you can do that. We know that for the value return functions, we do have to make sure that we provide a return statement. So this one's void, this one's void. That's not a good example. I think it was while. This one, right? So return integer, then we have to return something to make sure that our function works properly. We can test it, and then whoever's using our function can get that data in the sum of squares and do whatever they need to do when they call our function. So I'm pretty sure that you all are aware of this by now. Okay, also we know that a function, make sure, function parameters, yep, can take no parameters or can take one or more parameters. And the parameters can be whatever type we need to feed into that function. In this case, we have an integer, but we can also have double or character. Like that's fine, like we can mix them. There's nothing keeping us from doing that. In Python, like parameters, you only pass them and use them, and you never had to worry about different types of parameters that you would send into Python functions. That's not the case in C++. We have to worry, or we'll learn about different types. So we've been using syntax like this. So this is arguments that are called by value, and we'll explain that. And then we have arguments that are called by reference, and then we have arguments that are called by pointer. So three different types. The reference and the pointer, they more or less work the same. But we will get into that. But before we get into that, we have to understand how memory works and how memory controls how functions are executed. So we have we run a program. The operating system gives us stack memory, heap memory, data memory for some values that we need to, like the number 10, like it needs to go somewhere, right? Like int equals 10. That 10 needs to go somewhere, right? So that's what this means, data. And then for our code, and then global memory. Those are for global variables, and global variables are available to any function, and we'll get into that in a few. And just to refresh your memory, the stack is last in, first out, meaning like main is the first in, so it'll always be the last out. And any, like for example, let me trace this code right here, the for ranged. When this program runs, first thing in memory is main, the main function. It's loaded onto the stack. It'll get a block of memory for main. And then I call loop string with for range. For now, I'm ignoring this, okay? Then that function will get its own memory block in the stack, and we'll go into detail how that works. The stack is small, about 1024 kilobytes. It's continuous, meaning it'll always give us the next memory address, okay? Unlike the heap or the free store, it's random memory. It's very large, to about 2 to 4 gigabytes. And it's up to an algorithm that controls the heap that determines like where we get our chunk of memory from, okay? So we don't dictate that. We don't know, like it'll be random depending on how large of chunk we need. And just imagine, like if our program's large, at any one time the heap can have a lot of blocks used. So then there's an algorithm that's like, okay, you need three characters or 3 bytes for Joe. Let me go find a chunk of 3 bytes, and then they give us those 3 bytes for us to use, okay? And we will focus on the stack and the heap, okay? So if we go into the stack steps, let me see here. First step is a function is pushed onto the stack with its state or with its variables, right? So when main is running and we need to execute loop string with for range, then we need to remember, or not we, right? The compiler. The compiler needs to know, like, after I execute this, like, where do I come back and continue executing? So that's what this means, like push current function state to stack, meaning like I need to remember that there's a variable named Joe. That way when I come back here, like I know to recreate or make sure that that data is still valid, okay? Push return values to stack. So in this case, I don't think we have return values for loop, so that's not necessary. Push function arguments to stack. So we do have a function argument name, so that one has to go into memory somehow, so that when this code starts executing, the compiler can grab it from memory, and then we can run this piece of code, okay? That's what that means. Push return address to stack. So like, if we look at the stack here, say that main occupies this block. So then when we jump, or not we, when the compiler jumps to the loop with for range, and it finishes executing, then it has to know what address it's going to go back to so that main can keep on running. That's what that means. And then I come back over here. And the final is jump to function location, right? So if it knows where it needs to go, it finishes executing here, and then it's like, okay, so let me jump back to main. And since it stored that return address, then it'll go back and it'll continue executing properly. And, so it knows where to go back and continue executing. To handle all that information, we will work with activation records. And an activation record is what goes onto the stack, right? So if we have the stack here, when main runs, there'll be some memory addresses reserved for main, and then this block here will be the activation record for main. And then when we call the next function, I'll just say loop with blah, then it'll have its own memory. And that'll be its activation record. So let's see what that activation record holds. Okay, so activation record, it holds, like in this case, it'll hold the main function state. That's one thing it keeps track of. And then return value if needed. In this case, we know we don't need a return value from the loop function, but there's memory, and this activation record will go in memory, okay? Right there. And then we have a function argument. So then there's memory that will be used for function arguments. Let me look at the function. Loop str. Okay, so let me put that here. So str would be a function argument, so there's memory to store that value. And then we have the return address. Where do I need to go to continue executing? So return address. And then so when an activation record is loaded onto memory, this address might actually be like some big address. I don't know, just to pick a number, I'm just going to say like 1 million. What this pointer does is it allows an activation record to have its own virtual address, meaning like this could be like 0 for let's say maybe 16 bytes here, so that would be for 12, and then 4 for the return address. So instead of having to worry about keeping track of like millions, then it just uses small numbers to make it easy for it to keep track of itself. So the base pointer thinks that that's the only address in the system, when in fact like this over here, right? So say this is maybe like 40 bytes hypothetically, and over here we have like 4 gigabytes of RAM. then the activation record thinks there's only 40 bytes of memory that ever exist in the universe, right? So that's to make it easy. And then we have a local function variable. So local function variables. And if we go look at this function, local variable might be like this AutoS, right? So the loop is looping, and then it might be like this. Or if we have some number here, so that would be a local variable. And as you can see, if we go back to the diagram, all of that would be in this block of memory. I just made it larger so that you all can see like what goes into loading a function. Questions here? So while you all think of a question, so why am I covering this? This is going to help you understand the different types of function parameters that we use in C++. With activation records, we'll be able to get C++ code, map variables, function arguments onto an activation record, and then we'll get a visual of how that activation record goes onto the stack. And then I'll be able to explain, like, this is this type of variable value, this is a reference parameter, and then this is a pointer parameter, and I meant value parameter, not. So questions? What does the base pointer, I forgot what the E stands for, but it's base pointer, meaning like it'll just worry about keeping track of addresses in this activation record. And then we have a stack pointer, right? So what, but you'll get into that when you get into computer architecture or the assembly language piece. Like, you will appreciate like a high level language. Okay, so let's use an activation record to understand a variable scope. Okay, so let me pick an example here. This one was not really a helpful example. Let me look at some code and then I'll be able to pick one. Maybe the while loop. I think this one serves better, yeah, because there we have local variable here, and then we have a parameter. Yeah, so this one will work better. So let's and then let me look what main. Okay, let me look at main for a while. Okay, so let me. We don't want to worry about this. We want to deal with the return value, and then we call sum of squares with num. Okay, so let's map this code to an activation record for a main, and then an activation record for sum of squares, and then you'll understand why this num is different than this num, and how this sum cannot be accessed in main. Okay, so first let's map main. So we go to variable scope. So we'll have main here, and then over here we'll have sum of squares. And here is the stack, okay? For now, we won't dive into the stack for now. We'll try to understand the activation record first, and then we'll dive into the stack. So we'll have a record for main first, okay? So this is the activation record for main, and goes into block of memory on the stack, okay? and then we look at the state. So let's look at the code. So we have num equals 5. Okay, so then 1, 2, 3, 4. So we have state. I don't have this guy's memorized. Return value. Arguments, so function arguments. I guess I'll do this. That way I don't have to rewrite those for over here. Okay, function arguments, return address. Base pointer, which we really don't have to worry about. We're not going to cover how that works. And then local function variables, that's what we are interested in. Local function variables. Okay, so we'll focus on local function variables and function arguments, okay? That's what we want to cover. So function arguments for main, there's none, right? So we come back here, then look, there's no function arguments for main. Local variables, num equals 5, so we have num equals 5. And remember, this one has its own virtual address, and it's somewhere here, like in this on the stack, somewhere here, okay? And then num is created, and then sum of squares is created. So as soon as sum of squares is created, there's another activation record that's created. And then this one is loaded onto the stack, and this will be the sum of squares record, okay? And it has also its own region of memory. So what do we have to map? We go and look at the function signature. We have a function argument num, okay? So function argument, so we have integer num. That's an integer, it's 4 bytes. And this is also an integer. From here, you all can deduce, right? Or imply that, oh, wait a minute. So yeah, that's right. So if this num exists in this region of memory here, and this num exists in this region of memory here, they're not the same num, right? And that's important for students who have issues. Like some students think that this num is fed into this one, and then that this num is this num. But hopefully from this drawing here, we can deduce it that they are not, right? So they are not the same nums. They're two separate nums. One lives here in main, one lives here in sum of squares. Okay, so what else do we need to map? We go to while.cpp, so sum. Oops, I have the eraser. Okay, so here I wanted to do this. So we don't worry about the base pointer, but we know that we have integer sum equals 0, and that one's also somewhere over here. So we come and look at this. So then now you understand that this sum, no matter how hard you try, you will not be able to access it over here. And I've purposely named this num the same as this, but it is not the same variable. and you should be able to see that from here. So this is main local function variables, num equals 5. It's this one. And then we have a function argument. It's on the activation record for sum of squares in num function argument. So notice they are two different variables that have the same name, but they are in different regions of memory on the stack. Is it common for variables to share names? I don't think it's common, right? I just do this. I don't know if it's common or not, actually. In my case, sometimes they are, sometimes they're not, right? But I purposely name them the same just to point this out, that it's not the same variable. They live in different memory regions or blocks. And let me come back to the image, and that was a question from Tom. Okay. So questions here, like, and this, it's important you understand this because we're going to get into the different types of parameters in the next few lectures. And we'll map up activation records for those to show you how those work. But so far, like this, is this understandable? That nums, let me see here. We don't have to worry about it, as we'll always name it something differently. Well, you do have to worry about it when we get to reference parameters and pointer parameters. Even if they're named differently, you'll see that, you'll see how those work, and then you'll see like, oh yeah, I do have to worry about it. Okay, so here I named them the same just to make sure that I drill that point home, like they're not the same. Okay, so no questions here. Okay, so then we go back and trace the code. So sum of squares starts executing. And like I said, as soon as it starts executing, sum of squares is loaded onto memory. And recall that this structure is last in, first out, meaning as soon as that guy finishes executing, it'll be removed from memory and main will still be in memory. So we come back to the source code, sum of squares. Sum of squares executes, return sum. So we need space for the return address, right? So let's look at this return value. So this would be sum, the return value. And then it's returned. Oops, I wanted to go here. And then the next statement is here. But if we're going to do something with our data, like maybe C out, right, so that I don't have to map any more variables. So C out, sum of squares. Main would get the value from this return value activation record, and then it would feed it into C out, and then C out would be able to display the value to the screen. Okay, so that's important to understand also. Main has a return of 0, which I didn't map, so then we need to, so that would be 0, right? Return value of 0. So then C out displays, what's that, was 55, right? 55 to screen. As soon as sum of squares returns back to main, then this is removed from memory, right? Even this activation record, it's gone, like it's gone. And then main is still in memory. And then we have return 0, program starts exiting, and as soon as our program exits, then main is removed from memory, and then the memory is free. And that's how the stack helps manage our code, right? A simple example, and we'll continue with more examples, right? As we continue progress with our deep dive into the functions. So this is actually very important. The activation records, it'll help you understand how the different parameters work, right? So as I said, there's value parameters, reference parameters, and then there'll be pointer parameters. And with the activation records, we'll diagram them in memory to make sure we understand how those are working. Okay, so let me come here. For now, I will skip static variables. I'll come back to them, okay? And right now, I want to briefly mention default arguments. So we're here in the while loop. So I'll go to the header. So I'll say like, okay, so if I do not get a value, I just want to default this parameter to the value 3. By doing this, then I can say sum of squares. So if I don't send in a function argument or primary value, then C++ will be like, oh, okay, so I'm going to use 3 as a default value for num. And that's convenient because sometimes like we want a value to have a default value unless it's overridden by sending in a function primary value. So this is helpful in this case. Like we can go ahead and go here. And let me find this example. While running terminal. So 14 and 55, and maybe I need to make sure I do this. Running terminal. So now it looks better, right? So this executes, outputs the number 14, and then this executes and outputs 55. So questions here? CPP? Yeah, the CPP does not change. We put the default parameter in the header. Yeah, but I'll go there. There's the CPP. Okay. Okay, so let me go back over here. And I don't want to jump in front. I want to go further than we are. I'm in the other class, so let me see here. Parameters. Okay, so let me elaborate a little bit more on variable scope. Okay, so we'll continue with this example. Sum can be read in that block, even in the while loop. What the compiler will do, if we say some, it'll look for some in this range of code. If it doesn't find it, then it's not in the while loop scope. Then it'll try to find it in the sum of squares block. It finds it, and now it's like, oh, okay, so the initial value is 0. Then it can work with it, and then it returns it, right? So this is known as a local scope. So if we go from local function variables, right? So this is the local scope for a function. If it does not find some in the local scope, and we go back to our diagram here, stack, we have the stack, heap, but then we have global scope. So there's memory available for global variables in our code. So then it would try to find it in the global scope. So let me see here. How can I show you that? Let me see here. So we want to break the code here. So we break that code. So now we know it's like, oops, something's wrong. And let's see here. Auto sum equals 0. And notice, so now we can say, oh, okay, so it looks here, doesn't find it here. It looks here, doesn't find it there, then it'll go into the global scope, and then it's like, oh, okay, I find it, and now notice that our code should still work. Maybe we should run this program just to make sure. So run in terminal. So our code kind of works, but we have 14 and 69, so that was what, 55 plus 14. So notice why global variables are evil, right? So yeah, I guess what we could do here to prevent that is we could say sum equals 0, but global variables are not recommended. They are recommended like for read only values, maybe like for the tax rate, or for payroll tax rate, something like that. We make them const, and then they are read only and nobody can change them. The point here is we have global variables, function local variables, and then structure local variables. Okay, so questions here? So I'm going to change this code back, right? Because I don't want to, it's not a good programming practice. So this is what we want to do here. Yeah, we can define variables in main, and we should be able to access them in other pieces of the code. But they are evil, like stay away from them, unless you're doing the read-only ones. Because, I mean, our programs right now are small, but just imagine like global variables in a program with at least like maybe 500 lines of code. Like any one of those lines can change that global variable. And then how do we test that? So that's why we want to keep the variable used to as small a scope as we can, because they're easier to control and test and validate. Okay, let me go back here, make sure I didn't forget anything. So any questions on the memory, on the stack, heap, activation records? So the activation records, make sure you understand them, because there will probably be a question on the midterm that's where I put like a snippet of code for you, and then you have to create the activation records for that code. So you'll only focus on arguments and variables, right? But still, and return values, but still, like, you have to make sure you understand, otherwise you're not going to be able to complete the activation record. So let me go here. So I'm going to give you a problem, and you're going to have to like do something like this, where like you explain like main loads, and then the next function loads, and these are the values in the activation records. And then once this one executes, this one goes out first, right? Like you might have to say like goes out first and then last, right? Something like that, so that I know that you understand how the code is working in memory. So any questions on that, any of this? Let me look at the calendar. I don't think I have any assignment for today. Yeah, we'll have one on the next class. So there's no questions, and I want to stop here, and then we will continue in the next class. I will cover static variables and then the different types of function parameters and how we can use them to our advantage. So if you don't have any questions, and that's it.